All right, everyone, welcome to our 4th week of the Math E15 Graduate Seminar. This is the last week that I'm going to be in charge. The remaining time will be devoted to you guys being in charge and presenting your lessons, teaching the rest of us. As promised, this week we're going to do an example where the algebra doesn't work out perfectly. So you remember that last week, all 3 proofs that we did, the function was either linear or linear just with one absent point, meaning essentially linear. And that's why we were always able to work out the algebra perfectly to find the delta in terms of the epsilon and hit the corners perfectly in the language of that app that we talked about before. So now this function, f of x equals square root of x, that's clearly not a linear function. So in fact, if we draw its graph, something like this. So it's never undefined anywhere. So when x approaches 16, what do the y values approach here? 4, right? This graph is perfectly continuous. So as x gets closer and closer to 16, y gets closer and closer to 4. So then we want to prove this. So as usual, the person on the street gives us an epsilon, meaning he's going to say we can go up epsilon units from 4 and down epsilon units from 4. And we've got to find a delta to make the graph stay in there. So given epsilon, we must find delta such that what? In this case, if 0 is less than absolute x minus so here, this is measuring how far we're going away from 16, right? So the distance between x and 16 is less than delta, then f of x minus the limit of 4 is supposed to be less than epsilon. So we're going to try to, so you can see here that maybe if we go back to here, 16 minus delta, and if I go the same distance in this direction, 16 plus delta. As long as the x's stay in here, the y values stay where they're supposed to in that little epsilon band. But you can see because this graph is concave down that we're not going to hit the corners perfectly because the graph does not go linearly. So in this case, if I hit this corner perfectly, then we don't hit that one perfectly. But that's OK. We just have to make sure that all of the y values stay where they're supposed to be. And so even here, the y values are underneath that 4 plus epsilon. So before we can write the proof, just like last week, we have to do the scratch work like we're going to do here. So again, we're trying to prove a statement of the form if p then q. So for the scratch work, we work backwards, and we start with the q part. We start with f of x minus 4 less than epsilon, and try to work backwards. So f of x minus 4 less than epsilon. And remember, somehow we're trying to work backwards to get an absolute value of x minus 16 at the end. So our usual step is to just replace f of x by its formula. So what is f of x here? Square root of x minus 4 less than epsilon. And whereas last week it was always sort of obvious what we were supposed to do, like factor or get a common denominator, it's not quite as obvious this time, is it? Anybody have any suggestions on what we could do? We would like to get an x minus 16 in there instead of a square root of x minus 4.
Can you multiply square root of x over square root of x?
Multiply by square root of x over square root of x?
Yeah.
So you're suggesting multiplying by 1 in a clever way. And I agree, we are going to multiply by 1 in a clever way. But if we just multiply by square root of x over square root of x, we'll get the x, but then we'll get 4 root x, which we don't really want, right?
So why not we square both sides?
Square both sides? So if we square both sides, will that still get rid of, will that end up with just an x minus 16 in the top? I mean, first of all, we have to be very careful with absolute value of things when we're squaring. But if you square something like this, when you FOIL it all out, right? You'll get an x at the start, but then at the end you'll get a plus 16, and you'll get some stuff in the middle that you don't want. But there is a there is a technique, in fact, that we saw in the non-seminar portion of the class when we did a derivative during the 3rd week. We had something very similar to this.
The conjugate?
And we multiplied by the conjugate. So we multiply by 1 in a clever way. In this case, multiplying by square root of x plus 4 over the square root of x plus 4. That's called multiplying by the conjugate. Because now when I multiply these terms out, the middle terms cancel like they weren't going to do if we were just squaring. Because now what do we get on the top? Just what? X minus 4 squared, right? So x minus 16 over the square root of x plus 4. And that's great, because x minus 16 is exactly what we wanted. People agree with that? So multiplying by the conjugate came up again. But this is still not quite as clean as we're used to seeing, right? If this had been last week, when everything was working out perfectly, on the bottom, instead of root x plus 4, we would have just ended up with what?
X minus 16.
Well, we would have had an x minus 16 on the top. But when we did the problems last week, the part other than the x minus 16 was always just a constant. So, for example, if this had been something similar to last week, we would have just had a 4 on the bottom. And then we would have just multiplied the 4 to the other side and be done, found our x minus 16, right? But it doesn't work out so nicely this time. We really wish that this square root of x weren't there, don't we? Then it would be easy to do the algebra. Because I can't, if I move this, try to move this entire denominator to the right side, then my delta all of a sudden is depending on x, which it's not supposed to do. The delta is supposed to only depend on epsilon, meaning I need to get over here only the letter epsilon and numbers, no x's.
Also no variable on the side of epsilon.
Right, so if you think back to what we did last week, always over here, we always had just epsilon and a number, like epsilon over 6 or epsilon over 3 or something like that. So sometimes, when you want something to be true, you just have to say, well, let's make it true. So we wish that this square root of x weren't there. So leave a little space here, but I'm going to remove the square root of x. Because this is something nice and clean that we could handle. Pretend that I hadn't written that there. Let's look at this. How do these two fractions compare? This is the fraction I don't like, but that I'm stuck with working with. This is the fraction that I wish I had. Which of these fractions is bigger? The one on the left or the one on the right? The one on the right is bigger because it has a smaller denominator, right? Because we know square root of x can never be what kind of number? We talked about square root as a function, and the whole planet has agreed that it will never give a negative output. So this square root of x can't be negative, meaning that we're taking 4 and we're adding something which is at least 0 to it. So this fraction is the bigger one. So would you agree that if I can make this quantity less than epsilon, then this quantity will have to be less than epsilon as well?
Yes.
Yes, right? If I make this bigger thing, which I can easily manipulate, less than epsilon, then this smaller thing will also be less than epsilon. So if we make square root of x minus 16 over 4 less than epsilon, we'll also have what we want, namely square root of x minus 16 over the square root of x plus 4. Did I say square root? I mean to say absolute value. Absolute value of x minus 16 over square root of x plus 4 will also be less than epsilon. Does everyone agree with that?
Yes.
And this is something that we can do pretty easily. So saying that absolute value of x minus 16 over 4 is less than epsilon is simply the same as saying absolute value of x minus 16 less than what? Less than 4 epsilon, right? I mean, we're sort of skipping a little step here. Like when we were doing it really slowly last week, we would first pull out an absolute value of 1/4 and then multiply that to the other side. So that's 4 epsilon. So what should our delta be? So if you think back to the scratch work we did last week, whatever this is our delta. Because we want absolute x minus 16 less than delta, and that's what we've got. Absolute x minus 16 less than 4 epsilon. So someone asked last week, I can't remember, if it's ever the case that delta is bigger than epsilon, and here's an example where it is. Last week we always ended up with like epsilon over 2 or epsilon over 3 or epsilon over 6. So all the ones that we did last week were linear, and they all had the same sort of straightforward algebra. And when we get to a square root function, any square root function, you're going to do the similar algebra to this. So the first time you see something like this, it's a trick, and then afterwards you own it, and it's a technique. So now you can use this technique anytime you want to do a limit involving a square root. So now let's do the proof. So remember, the person reading the proof hasn't seen all this scratch work. So we're going to be nice to the person reading the proof and lay out exactly what we're going to do. So again, the person on the street gives us an epsilon. That person can be extremely strict and give a very, very narrow band for us to keep the y values in. It's our job to find a delta so that when we stay near 16, right? Because remember, absolute value measures distance. So this is the distance that x strays away from 16, as long as that is less than delta. Then the distance that the y value strays up and down away from 4 will be less than the epsilon that the person on the street gave us. So if we look at the picture, we're going to keep the x's in here. And by doing so, we're going to keep the y values in this epsilon band, the error band that the fellow on the street is allowing us. And since we've done the scratch work, we know to choose delta to be what here?
4 epsilon.
4 epsilon. And so now in the proof, we're trying to prove a statement of the form, if P, then Q. So we start with the P part. We start with the part that we're assuming. And then we just need to do enough algebra to end up with fx minus 4. So now, 0 less than absolute x minus 16 less than delta. And let's just remind ourselves one last time, what is this 0 preventing x from equaling? If x minus 16 in absolute value is strictly greater than 0,
16.
X cannot equal the number 16, right? But and that's because we don't care about what the limit, when we're computing the limit, we don't care about what happens at 16. We only care about what happens near 16, right? We've been saying that since the first day. But in this case, did we ever use the fact that x wasn't 16? Was anything funny happening at x equals 16 with this function? No, this graph is perfectly continuous, right? So in fact, if you look back at this algebra, we never needed to know that x couldn't be 16 when we were doing this. But we did need that sometimes last week. Meaning we can drop this 0 right away. So we can say this implies x minus 16 is less than our delta, which we've decided is 4 epsilon. We didn't need that 0. It's perfectly OK with us if x ends up equaling 16 in this problem. So now we're going to do the scratch work backwards. So we're going to go from this line, x minus 16 less than 4 epsilon, work back to this line by dividing a 4 each side by 4, technically by absolute value of 4, but absolute value of 4 is the same as 4. And so we had a one-sided arrow going from here to here, because these two statements were not exactly equivalent. But now this statement and the one below it are exactly equivalent, so we're going to do the double-sided arrow there. And now we're going to really impress the person reading the proof, because we're going to say that since we know this is true, right, we know absolute x minus 16 over 4 is less than epsilon from over there, we're going to make the denominator even bigger by putting in a square root of x. So this statement implies, but is not equivalent to, this next statement, x minus 16 over square root of x plus 4 less than epsilon. Because what have we done? We have made the denominator of the fraction bigger. And we make the denominator of the fraction bigger, that makes the fraction even smaller. So if this big fraction was already less than epsilon, then this smaller fraction is even more less than epsilon. That is to say, it's still less than epsilon. And the only reason we know how to do that, the only reason we knew we ought to do that, was because we had done this scratch work and made this observation here. So now it's like we're up to this point in the scratch work. And now we're going to do something really crazy, because we are going to take this nice, seemingly simple-looking expression of x minus 16, and we're going to factor x minus 16. Because that's what our scratch work tells us to do. We're going to say, no, we don't like x minus 16. That's too simple for our tastes. We want to make it messier. We're going to factor x minus 16 into what? Into square root of x minus 4, square root of x plus 4. Seems crazy, and for those of you who are math teachers out there, you can tell your students that you factored a linear function there, a linear expression, into two pieces that actually made the linear expression look even worse. And the reason we knew how to do that was because back here, somebody had suggested that from this line, since we wanted to get an x minus 16 in the numerator, that we multiply by the conjugate. And now we are sort of undoing that multiplying by the conjugate. We are factoring that x minus 16. And that's good, because what can we cancel now?
Square root of x plus 4.
Square root of x plus 4. And we should, again, think just like last week. We have to be sure that we're not canceling something of the form 0 over 0, right? And we can only be canceling something of the form 0 over 0 if square root of x equaled what number here?
16. No.
If the square root of x equaled what number, would we get 0 on the bottom? This is not possible, but what would have the square root of x have to equal? Have to equal minus 4. But square root of x is a function, we've all agreed, and it only gives non-negative answers, right? Square root of 16 is only 4, never negative 4. So we can, with good conscience, cancel those. So we get square root of x minus 4 less than epsilon. And we're just following our scratch work backwards. Square root of x is f of x minus 4 less than epsilon as desired. And so that proves that limit. So last week, the algebra was very straightforward. It was hard to see anything other to do than what we did, the right thing to do. This time, we needed to be a little bit more creative. And basically, as you get into more and more complicated functions with these limits, you have to become more and more creative. So there's a different technique for quadratics, for example, different technique for sines and cosines. And some of the lesson ideas that you guys might choose to present will involve using those techniques. Any questions on our last limit like that before we go and prove something completely different? All right. So if you want to prove that a limit doesn't exist, the standard technique is to use this thing called proof by contradiction. And proof by contradiction works by assuming the opposite of what you want to prove. So if you want to prove that the limit doesn't exist, you start off by assuming the limit does exist, and then you do a series of logically correct steps until you arrive at something that you know is impossible, namely a contradiction. It could be like 0 is less than 1. I'm sorry, 0 is greater than 1, or something like that.
I really apologize. Does anybody have a pencil I can borrow?
This is great on live TV going out all over the world. We have somebody coming in and asking for a pencil. That is good TV here. All right. At any rate, so the idea is, so maybe we'll edit that out in the post-production. If we're trying to prove something by this method called proof by contradiction, we assume the opposite of what we're trying to prove and then show that leads to something impossible. So I have an example here for us to do that we will do this proof. That we're going to prove that the square root of 2 is not a rational number. So for that, we need some definitions. So they're all here on the piece of paper. I won't write them out for you. They're on the handout on the website. We need a couple definitions here. So we need to define what we mean by an integer being even and odd. So this example has nothing to do with limits. This is just an example to illustrate in a very important and famous way how you do a proof by contradiction, just so that we understand the technique if you need to use it to prove that a limit doesn't exist later. So we have a definition of even and odd. And I know that probably most people think about defining even in terms of something about dividing, right? You probably think, oh, a number is even if when I divide it by 2, I get no remainder. And that's right, but it actually turns out to be more mathematically convenient to use this this better definition that we've got here, which is to say that an integer is even if it is 2 times another integer. That ends up working much more nicely mathematically in proofs. Similarly, an integer is odd if it's 2 times another integer plus 1. That's what we've got written on here. And then finally, there's definition of what it means to be a rational number. Rational comes from the word ratio, so it means you're taking one integer divided by another. So like 3/7 is an integer. 3/7 is a rational number because it's one integer divided by another. Pi over 2 is not, because pi is not an integer. So we are also going to need to use what's called a lemma here. So a lemma is a little helping theorem. And our lemma that we're going to use in our big proof is going to be the not earth-shattering statement, but we'll need it. If n squared is even, then n is even. Do you believe this statement to be true? Think of all the perfect squares you know. 0, all the even perfect squares you know. 0, 4, 16, 36, 64, a million. In every case, their square root, the thing that's being squared, was an even number. So based on empirical evidence, it seems like this should be true. Let's see if we can now prove it. Now, trying to prove this statement directly is actually quite hard. If you just start out by saying n squared is 2 times some integer, it's really hard to know what to do next. So instead, we are going to prove what's called the equivalence. We're going to prove an equivalence statement. And in this case, so we're going to use this other word here. This word we're only going to use once, this word contrapositive. We are not, this is different than contradiction. Contradiction is what we'll really need to use a lot of when you're proving a limit doesn't exist. But to prove this particular lemma, we're going to prove its so-called contrapositive. So if we have a statement of the form if p then q, if you take a logic class, there's this thing called the contrapositive, which says if not q, then not p. And those statements are logically equivalent. So let's see if we can come up with a real-world example to understand why those two statements should be equivalent. So suppose that my statement is my policy in life. This is not my policy in life, but if it's raining, I am indoors, so I'm staying inside. Okay, suppose that's the rule. So anytime that it's raining, I stay indoors. So consider this statement. If it's not raining, sorry, no, that's not what I want to say. If I'm not indoors, if I'm not inside the house, so if it's raining, then I'm indoors. If I'm not indoors, what do you know about the weather situation? You know that it cannot possibly be raining, right? So if I'm not indoors, then it's not raining. So this first statement was of the form if P, then Q. This statement, the second one, that's exactly logically equivalent to it, is if not Q, then not P. Those two statements are saying exactly the same thing. So sometimes in math, when it seems like it's hard to prove a statement of the form if P then Q, we instead prove it's contrapositive. So what is the contrapositive of this statement? If n squared is even, then n is even. The contrapositive will be what? If n is not even, and do we have a word for not even? We're talking about integers here. Odd. So if n is odd, then n squared is also odd, right? That means n squared is not even, so n squared is odd. And as we'll see, this is a much easier way to prove our original statement. So what does this mean? If n is odd, how can I write n? By our definition of odd, n equals what?
2n plus 5.
2 what letter did you say?
M, sorry.
M, right. We should not use the same letter. We should not have an n and an m there. 2m, any other letter. 2m plus 1, where m is some integer, right? That's what it means for n to be odd. But we don't want to end up talking about n. We want to end up talking about what? N squared. So if n is odd, that means n equals 2m plus 1. So n squared must be 2m plus 1 squared, right? And I'm hoping that n squared is going to be what kind of number? Odd, right? So somehow I want to show that this is also of the form 2 times an integer plus 1 more. So let's see if we can do this. If I multiply this all out, I get what? 4m squared plus 4m plus 1. And I'm hoping that I can write that as 2 times an integer plus 1. So can you see what that integer will be in terms of m? We just brought this 1 down, and we sort of factored a 2 out of this, right? So what can I write here? 2m squared plus 2m, right? So we have now written n squared in the form 2 times an integer plus 1, meaning m squared is what kind of thing? N squared is what kind of thing? Is odd, which is what we were expecting would happen, right? And you might want to think a little bit about how you know that this thing 2m squared plus 2m is actually an integer, right? M and 2 are both integers, and you can convince yourself that if you add or multiply integers, you always get an integer as the output. That's not true if you divide. But we didn't do any dividing here. We just did multiplying and adding. And if you multiply and add integers as many times as you want, you always get an integer back. So this is our proof of the lemma. So this lemma is somehow going to help us prove that the square root of 2 is an irrational number. So that's now our big theorem. And I will actually call it a theorem because it's that important. The number square root of 2 is not rational. That's the theorem we're going to try to prove now, using our lemma along the way. And you might be wondering, why did I say the number instead of just writing square root of 2 is not rational? Many mathematical writers follow the convention that a sentence should not start with a number or a symbol. So many mathematicians, on seeing this, would cringe. And some would do more than cringe. They would be very, very upset. They would not like to see that. It comes from, you can imagine the confusion that might arise. If you've got some sentence that's going along, some words, and it ends with a 1, and then you put a period, and the next sentence starts with the number 2, and then there's some more words, you might get confused. You might think that was 1.2 along the way, right? When really this is a full stop in the British speak, meaning the end of the sentence instead of a decimal point. So that's the reason that we don't try not to start sentences with symbols. OK. So we're going to do this method of proof by contradiction. And we're going to be nice to the reader, meaning we're going to tell the reader we will do a proof by contradiction. As you get into more and more advanced math classes, the people writing the proof will not be so nice. And you might get a certain shock at the start of the proof, where the very first line in the proof is the person stating the exact opposite of what the person is trying to prove, because they are using this method of proof by contradiction. So if we want to prove that root 2 is not rational, we're going to assume that root 2 is what? Right. We're going to assume that root 2 is not rational. But a simple way of saying not rational is rational. And so now we use our definition of rational, meaning we can write it as a ratio of integers. So root 2 can be written in the form p over q, where p and q are integers. And anytime that you write a fraction of integers, you can always simplify it. I mean, you might be able to simplify it, right? Like if I wrote, I don't know, 32 over 6, many of you would instantly simplify that to 16 over 3 by canceling the common factors. So you can always, any rational number can be written where p and q are integers in lowest terms, meaning sharing no common factors. So our integers with no common factor. So in other words, if you started with a p over q that did both have a factor of 5 in them, you would cancel the 5 and put it in lowest terms, just like you were probably taught to do in grade school. And this number q cannot equal 0. So we want to prove the number is not rational. We assume the number is rational. And we hope that this is going to lead to something impossible. Because if it does, then that will mean that our assumption must have been wrong. As long as once we assume something and then we do perfectly legal, logical steps all along the way, if we arrive at something impossible, that means that our original assumption was the only thing that could have been wrong. OK, well, we've got this equation. It's got a square root in it. Let's get rid of the square root. What should we do to both sides now? Square both sides. So now, if we square both sides, we get 2 equals p squared over q squared. So if you're like many students, you don't like square roots, so you're happy that we got rid of the square root. If you're also like many students, you don't like what else about this equation?
Denominator being q squared, too.
The denominator be, yeah. I mean, I don't like the fact that it's a fraction. So I could just multiply both sides by q squared. So now I don't have any square roots and I don't have any fractions. Agreed? Now we have to look back at our definitions. P squared is 2 times an integer. So that fits our definition of what word? Even. Thus, p squared is even by our definition of even. Right? P squared is 2 times some integer, so p squared must be even. But I think we have a lemma about p squared being even, right? The lemma says that if a number's square is even, then p itself must have been what? Even. Thus, p squared is even by our definition. And then our lemma says p is also even. So now we're sort of just following our nose. Just whatever we see something, we either use one of our definitions or our lemma. We came up with this brilliant idea at the start to do the proof by contradiction. Well, p is even means what? If p is an even number, how can I write p?
2m plus 1.
No, just
That would be odd.
I'm sorry.
2m.
Yeah.
So that means p equals 2m for some integer m. That's what it means to be even, right? Well, let's see what that consequences that has for our equation. So 2q squared equals p squared becomes what?
2m squared.
Becomes 2q squared equals 2m quantity squared, right? Which is the same as saying 2q squared. If I wanted to remove the parentheses, I would get what on the right side?
4m squared.
4m squared. And when you see something like this equation, this is crying out to have what done to it? Cancel a 2 from each side, right? Or q squared equals 2m squared. By the way, these ors are not like alternatives. These are just saying this is another way of writing it. So this is the same as this, which is the same as this. Now again, let's follow our nose here. Q squared is 2 times some integer. So what does that mean about q squared? Q squared is even. And I think we have a lemma about that. Our lemma says that if q squared is even, so by our lemma, q must be even. Right? We've just used our definition of even and our lemma repeatedly in this proof. But now we have actually got our contradiction, whether you realize it or not. We have found q is even, but we had previously found that what was even? P is even. But what was our assumption? P and q were integers with no common factor. But if we've just proved that p and q are both even, they have a factor of what? 2. So thus p and q share a factor of 2, which contradicts our initial assumption. So there was a lot happening in this proof, by the way. The whole idea of proof by contradiction is sort of an advanced thing to think about. We're using our lemma, we're using our definition. So if our assumption that root 2 is irrational has been contradicted, therefore it must have been false, therefore root 2 must be what?
Irrational.
Hence, root 2 must be irrational. And that's what we wanted to prove. So well done. And this is a very famous result. In fact, the ancient Pythagoreans, this school of mathematician philosophers back in ancient Greece, their motto was all is number. And they believed that everything could be represented by a rational number. One of their members came up with not this proof, but with actually a nice geometric proof of the same thing. He showed that if you draw a triangle, a right triangle, with two sides like this, 1 and 1, he came up with a geometric argument to show that the length of this side could not be rational. And this really caused problems. It upset a lot of people because this was they really believed all is number. That was the central philosophy, one of the central tenets of their philosophy. And he showed that that was not true, because you can just draw a simple triangle like that, and you've got something here that cannot be written as a rational number, cannot be written as one fraction, as one integer over another, no matter what you try. And he did this reductio ad absurdum argument, meaning it was a geometric argument where he kept drawing smaller and smaller triangles and ended up getting something that was impossible as well. Now, I will say, should say one thing about this method of proof by contradiction, which is that there are mathematicians. This method relies on something called the law of the excluded middle. We assumed that, I mean, we all took it for granted, none of you argued with me, that if this statement was false, sorry, we assume that if, we assume this statement, we assume that if the only two options basically are either false or true. So by showing that something isn't true, we said it has to be false. Or if something isn't false, it has to be true. Meaning we were thinking these are the only two options. There are mathematicians who do not subscribe to this law of the excluded middle philosophically, and therefore they would not believe in this proof. But if you decide that you do not believe in the law of the excluded middle, then you cannot do proof by contradiction, because that's the heart of the proof by contradiction, is that if something is not true, it must be false, or if something is not false, it must be true. There is no third option. And most mathematicians are happy with this assumption. They buy into the law of the excluded middle, but some don't. Just to make you aware of that. So the point of this was to see a nice proof, very important proof, very big result. You can also use the same method of proof by contradiction to prove that there's infinitely many prime numbers. You might have seen that. It's a sort of famous proof as well. You say, I want to prove that there's infinitely many primes, so I assume that there's only finitely many primes, and then you show that that also leads to a contradiction. The very same general method as this. But the reason that we wanted to see it for this seminar is that in several of the upcoming lessons that you guys will be presenting, it will be necessary for you to prove that a limit does not exist, and the best way to do that will be to assume that the limit does exist and then do a bunch of steps and show that that leads to something impossible, like 5 is greater than 8 or 0 equals 1 or something like that, and that will prove what you wanted to prove in the first place, namely that the limit does not exist. Questions or comments? So in 4 weeks, you have come to understand, I hope, pretty well, this definition that it took generations and generations of the finest mathematicians in the world to come up with and understand well, namely what it really means to say that the limit of f of x is L. We came up with this epsilon delta definition. That is the definition that mathematicians all the world around use. It's one of the big achievements of what's called real analysis, this definition that lets us rigorously prove what a limit is instead of the old thing with Newton and Leibniz where they would just say, oh, something gets really, really small and then we can ignore it. That was on very shaky ground, even though they got all the right answers. So I hope you have come to have a more firm foundation of what a limit is than Newton and Leibniz had, and you should be proud of yourselves. Thanks for watching.